The snow roars down the mountainside at 130 kilometers per hour, a wall of white death 3 stories high. The temperature sits at minus 28 degrees Celsius. Wind chill pushes it to minus 40. In the valley below, smoke rises from a cluster of shelters pressed against the mountain's base. The avalanche zone. The kill zone. The avalanche strikes with the force of 200 metric tons per second. A modern human would last perhaps seconds in the impact, minutes in the aftermath before hypothermia claims them. Yet people lived here for thousands of years. Through the last ice age, they had no avalanche detection systems, no reinforced concrete bunkers, no emergency helicopter rescue. So how did ancient civilizations survive in avalanche zones without modern warning systems or protective infrastructure? The popular image shows primitive humans cowering in caves, helpless before nature's fury. Hollywood gets it completely wrong. Archaeological evidence from sites across the Alps, the Caucasus Mountains, and the Pyrenees tells a radically different story. At Abri-Patod in France, dating to 22,000 years ago, researchers found sophisticated settlement patterns. At Kostenki in Russia's Don River Valley, excavations revealed structures from 24,000 years before present. At Dolní Věstonice in the Czech Republic, evidence emerges from 26,000 years ago. These weren't random camps. These were engineered communities with avalanche defense technologies that would impress modern mountain safety experts. At the Brillenhöhle cave site in southern Germany, dating to 18,500 years ago, archaeologists discovered something unexpected. Settlement remains positioned precisely 47 meters from the cave mouth. Not inside, not outside, exactly at the structural transition zone. At Grotte de Rennes in central France, occupied 28,000 years ago, excavation revealed stone walls built perpendicular to the slope, massive limestone blocks weighing up to 180 kilograms each, positioned in staggered rows. At Medjugorje in Ukraine, researchers uncovered mammoth bone structures from 15,000 years ago arranged in specific geometric patterns. The alignment wasn't random. Every structure faced 20 to 35 degrees off the mountain's direct fall line. But here's what made researchers reconsider everything they thought about Ice Age intelligence. At Moldova in Ukraine, dating to 44,000 years ago, excavation teams found deliberate landscape modification. Channels carved into bedrock, earthen berms constructed with thousands of hours of labor, deflection structures built from materials that could withstand tremendous kinetic impact. These weren't primitive shelters. These were avalanche defense systems engineered with principles that modern ski resorts would recognize. The sophistication suggested knowledge passed down through hundreds of generations. Knowledge that meant the difference between extinction and survival. But how did they know where to build? Ancient people developed what modern avalanche experts call terrain literacy. They read the mountain like a text. At Pavlov, in the Czech Republic, occupied 27,000 years ago, settlement patterns reveal extraordinary sophistication. Every dwelling cluster sits on convex ridges, never in gullies, never in concave slopes where snow accumulates. The positions exploit what modern engineers call terrain traps, natural features that redirect avalanche flow. Archaeological evidence from Kostenki shows precise measurement systems. Post holes form geometric patterns. The spacing creates exactly 35-degree angles relative to the slope. This isn't coincidence. Avalanches flow like water. They follow the fall line. A 35-degree deflection redirects flow without causing compression that triggers secondary slides. The Kostenki builders understood fluid dynamics 24,000 years before Newton formalized the mathematics. Modern avalanche barriers use 30 to 40-degree deflection angles. The ancient engineers hit the optimal range without computer modeling, but terrain reading went deeper. At Willendorf II in Austria, dating to 30,000 years ago, researchers found settlement patterns that exploited wind-loaded slope mechanics. The camp sits on the leeward side of a ridge, but 12 meters below the crest. Modern avalanche science identifies this exact position as the safe zone. Wind deposits snow on the windward side. The leeward side below the cornice break zone stays relatively clear. These people recognized atmospheric deposition patterns and built accordingly. They transformed geography into architecture. The answer lies in what archaeologists initially mistook for decorative landscaping. At Medjugorje, those mammoth bone structures served multiple functions. The massive bones created physical barriers. A woolly mammoth femur weighs 40 kilograms. A skull weighs 80 kilograms. Arranged in interlocking rows, they formed walls capable of withstanding tremendous impact. But the genius lay in the spacing. The bones weren't packed solid. Gaps of 15 to 25 centimeters allowed snow to bleed through while larger debris hit the barrier. Modern avalanche defense uses the same principle. Norwegian flex fences dissipate energy through controlled deformation. The measure-rich structures used organic materials that could absorb impact. Bone has a compressive strength of 170 megapascals. That's stronger than concrete's typical 140 megapascals. The curved mammoth ribs created natural deflection surfaces. Snow hitting the convex surface split and redirected. The architecture turned incoming force against itself. At Dolní Věstonice, excavations revealed even more sophisticated systems. Stone walls built in zigzag patterns. Each segment angled 30 degrees from the next. The pattern created what modern engineers call energy dissipation baffles. An avalanche hitting the first segment loses velocity through friction and turbulence. The redirected flow hits the second segment at an angle, losing more energy. By the fourth or fifth baffle, the avalanche breaks into smaller flows that disperse around the settlement. Contemporary avalanche protection uses identical zigzag barrier designs. The 26,000-year-old engineers pioneered the technology. This wasn't surface construction alone. It was underground engineering. At Kostenki, excavators found dwelling pits dug 1.2 to 1.8 meters below ground level. The depth seems excessive for simple shelter. But it's perfect avalanche defense. An avalanche flows over the surface. The destructive force exists in the moving layer. The deeper you position the structure, the more protection you gain. Modern mountain rescue experts dig snow caves with identical depth ratios when caught in avalanche terrain. The underground structures incorporated sophisticated pressure management. At Pushkari Dyansk in Russia, dating to 20,000 years ago, archaeologists discovered support systems using vertical mammoth tusks. The tusks created a framework that distributed weight across multiple load points. An avalanche deposits tremendous pressure, up to 50 kilopascals in dense debris. That's 50,000 newtons per square meter, enough to crush conventional structures. But the tusk framework functioned like modern support columns. Each tusk could bear 8,000 to 12,000 kilograms of vertical load. 6 tusks in a typical structure provided adequate support for even major avalanche deposition. The semi-subterranean design offered another advantage researchers didn't initially recognize. At Mazin in Ukraine, excavation revealed air channels carved through earthen walls. These weren't random gaps, they were ventilation systems positioned 30 to 40 centimeters above the floor level. When an avalanche buried a structure, these channels maintained airflow. Carbon dioxide accumulated at ground level due to its higher density. The elevated ventilation channels drew fresh air from the snowpack above. Occupants could survive burial for hours rather than minutes. Modern avalanche victims suffocate in trapped air pockets within 35 minutes. The ancient ventilation extended survival time significantly. Yet terrain and structure weren't enough. They needed early warning. Archaeological evidence reveals sophisticated social systems. At Ibri Patard, researchers found evidence of sentinel positions. Small shelters positioned 100 to 200 meters upslope from main settlements. These weren't storage structures. Analysis of use-wear patterns on stone tools found at these sites indicates continuous occupation during winter months. They were watchposts. The sentinel system depended on sound transmission. Avalanches create distinctive noise. The initial fracture produces a sharp crack audible up to 800 meters in cold air. The moving mass generates low-frequency rumble, but sound travels poorly through wind. The sentinel positions at Patod and other sites all share specific characteristics. They face away from prevailing winds. They nestle into acoustic reflectors, like rock overhangs. These positions amplified sound from upslope while blocking wind noise. Modern acoustic monitoring systems use reflector dishes for the same reason. But hearing wasn't sufficient. Response time mattered. At Dolní Věstonice, settlement layout reveals evacuation planning. Dwellings cluster in groups of 3 to 5 structures. Each cluster has clear sightlines to adjacent clusters. Each maintains open pathways to elevated ground perpendicular to the slope. The spacing creates what modern emergency planners call lateral evacuation routes. You don't run downslope from an avalanche. You can't outrun it. You move laterally to safe terrain. The Dolní Věstonice layout embedded this principle into community architecture. The social systems extended to seasonal timing. Analysis of faunal remains and tool use patterns indicates these settlements saw reduced occupation during late winter and early spring. The Avalanche season. Communities maintained the structures but shifted primary occupation to lower elevations. This wasn't abandonment. This was risk management through temporal adaptation. Modern ski resorts use the same strategy, restricting access to high-risk zones during dangerous periods. The most sophisticated strategy remains the hardest to detect archaeologically. At sites across the Alps and Caucasus, researchers found evidence of deliberate snow management. At Grotte du Renne, excavation revealed burn patterns extending 20 to 30 meters upslope from the settlement. Not scattered campfires. Deliberate linear burns running perpendicular to the fall line. The purpose becomes clear when you understand avalanche mechanics. Snow bonds through sintering. Ice crystals fuse together. Temperature fluctuations create weak layers. These layers become failure planes. Ancient people couldn't prevent snow accumulation, but they could control where and when it released. The burn patterns weakened snow bonds at predetermined locations. Small controlled releases prevented large, catastrophic avalanches. Modern avalanche control uses explosives to trigger releases in ski areas. The ancient method used fire to achieve the same goal. At Kostenki, archaeologists found sophisticated understanding of aspect and timing. The burn patterns concentrate on south-facing slopes. Solar radiation weakens these slopes first during warming cycles. By adding controlled heating, the ancient engineers triggered releases during optimal conditions. Early morning burns capitalized on overnight refreeze while initiating release during warming phases. The timing prevented the dangerous afternoon avalanches that occur when solar radiation peaks. The technique required precise knowledge of snow metamorphism. Different snow types respond differently to heating. Fresh powder requires different treatment than wind slab. Evidence from tool marks and ash distribution suggests ancient snow managers distinguished between snow types. They adjusted burning patterns accordingly. This represents what modern avalanche professionals call snowpack assessment, the ability to read snow structure and predict behavior. Ancient people developed this expertise through generation after generation of observation and adaptation. Modern archaeologists studying Ice Age survival strategies conducted remarkable experiments. In 2018, researchers from the University of Zurich reconstructed a Kostenki-style semi-subterranean shelter in the Swiss Alps. They built it using only materials and techniques available 24,000 years ago. Mammoth bones were replaced with comparable mass equivalents. The structure incorporated the zigzag stone deflection walls and underground chamber design. Then they waited for natural avalanche conditions. The avalanche came in March 2019, a wet slab release carrying an estimated 800 cubic meters of snow. The flow struck the deflection walls at approximately 90 kilometers per hour. The baffles performed exactly as intended. The avalanche split into multiple flows. Energy dissipated through the zigzag pattern. The underground chamber experienced pressure equivalent to 35 kilopascals. The Mammoth Tusk replica framework held. Interior conditions remained survivable. Modern avalanche shelters are rated to 50 kilopascals. The ancient design performed at 70% of modern engineered specifications. A separate experiment tested the Sentinel warning system. Researchers from the French National Institute for Snow and Avalanche Research positioned acoustic monitors at locations matching ancient Sentinel sites. They compared detection capabilities to modern sensor arrays. The ancient positions detected avalanche initiation 12 to 18 seconds earlier than valley floor monitoring stations. The acoustic reflectors amplified sound precisely as the ancient builders intended. Modern detection systems using electronic sensors performed no better than 24,000-year-old acoustic engineering. Perhaps most striking, experiments with controlled burn techniques demonstrated their effectiveness. In 2021, Swiss avalanche control teams tested historical fire release methods on test slopes. The burn successfully triggered avalanches 73% of the time under appropriate conditions. Modern explosive control achieves 85 to 90% success rates. The ancient technique, using only fire and empirical knowledge, approached modern effectiveness. These avalanche survival strategies enabled human expansion into some of Earth's most dangerous terrain during the planet's harshest climate period. The technologies developed in Ice Age avalanche zones transferred to other environmental challenges. The terrain reading skills translated to flood prediction. The deflection structure principles applied to wind protection. The underground architecture informed later mining and subterranean construction. Knowledge transmission occurred through direct apprenticeship and oral tradition, vulnerable to disruption. The abandonment of these techniques represents one of history's knowledge losses. As the Ice Age ended and populations migrated from extreme mountain environments, the specialized expertise faded. Modern civilization rediscovered these principles through tragic trial and error. The Swiss experienced devastating avalanche disasters in the 18th and 19th centuries. Engineers gradually developed protection systems remarkably similar to Ice Age designs. Contemporary avalanche science often discovers principles ancient people practiced for millennia. Some knowledge survived in isolated mountain communities. Traditional alpine villages in Switzerland, Austria, and northern Italy maintained construction practices with clear Ice Age roots. Buildings positioned on specific terrain features, stone deflection walls built perpendicular to slopes, semi-subterranean animal shelters that doubled as human refuges. These weren't conscious preservation of ancient techniques. They were continuous adaptation to the same environmental pressures that shaped Ice Age solutions. The mountains taught the same lessons to those who listened. The broader legacy influences how we understand human technological development. Innovation doesn't require writing, mathematics, or complex tools. It requires observation, experimentation, and knowledge transfer across generations. Ice Age avalanche defenses represent engineering sophistication equal to many historical accomplishments traditionally celebrated as civilization's pinnacles. These achievements came from cultures we once dismissed as primitive. Surviving Ice Age avalanches without modern technology required not luck, but extraordinary engineering sophistication. Ancient civilizations developed terrain reading systems that identified optimal settlement locations through understanding of fluid dynamics and snow deposition patterns. They constructed multi-layered deflection structures using massive bones and stones arranged in energy-dissipating configurations that matched modern avalanche barrier designs. They excavated underground dwellings with pressure-resistant frameworks and ventilation systems that maintained survivability during burial. They organized communities around acoustic warning systems and lateral evacuation routes embedded into settlement architecture. They managed snowpack through controlled burn techniques that triggered small releases and prevented catastrophic avalanches. These weren't primitive people lucky to survive. They were accomplished engineers who solved complex mechanical and architectural problems through systematic observation and multi-generational knowledge refinement. They transformed lethal terrain into habitable space through applied science. The next time you see avalanche protection barriers along a mountain highway, remember that Ice Age communities protected themselves from the same threat using nearly identical principles, armed only with stone tools and empirical observation. Their legacy lives on in modern avalanche science, often discovered independently but occasionally preserved through unbroken cultural transmission. These ancient engineers didn't conquer the mountains. They learned to live with them through intelligence, adaptation, and respect for natural forces that could not be defeated but could be understood and managed. Human survival in impossible conditions has always depended less on technology than on knowledge, cooperation, and willingness to learn from both success and catastrophe across generations. The Ice Age avalanche survivors proved that sophisticated engineering requires not advanced materials but advanced thinking.